everyone. How are you doing? We have our last lecture today. So we are going to look at notes and assignment. I'm good, thank you. It is Monday, week 12. Let me log on to Canvas. So if you get a chance, log on to Canvas. We will work on relations today, everyone. Hello. So check out notes and assignments in Canvas and we'll start in a few minutes. Yeah, I understand. I finished class and office hours. I was working on recording video till late. So Monday is always so busy. And then on Saturday, I attended the UCR event for Women in Data Science. It was pretty cool. Learn a little bit about, some of the positions out there, and then the tools that's used for machine learning. Oh, thank you. I visited my mother in Orange County. We had pizza. There are not a lot of restaurants that are open. Some outdoor, but we stayed home. I spent some time with her. My brother had to work, so he couldn't stay home and spend time with us. But yes, thank you so much. I hope you had the same thing. Everyone had a good Mother's Day. Time just flies by so fast. Next month will be Father's Day and then summer. Okay, check out your Canvas materials and then I will start in a minute. Hi, Jose. How are you doing? Okay, it's 6 o'clock. So welcome to our last lecture. I'm excited for you to finish the semester. Um, I will go over final review next week and the following week on Monday. We don't have any more lab to do. So this week, let me get into screen share and I can show you what we're looking at for this week. As some of you have already started checking out your assignments and your tasks for this week, we have an assignment to complete today, which relates to relations, and that's going to cover chapter 17. Some of the questions will be on the final and the last quiz. Next week, we will have another quiz, and we will work on final review. Okay, so I will post that. And final review is not due until later, but I can go over each question with you. So on Monday, that's going to be the plan. On Wednesday, starting this week, I will be on Zoom during our class time. And if you have questions relating to assignments, projects, tasks, you can pop in. Okay. Just a reminder, if you have outstanding assignments or missing assignments, they need to be submitted by before June 6th. Okay, I want to update everybody's grades. So going into final, I don't take any more late assignments. I will only accept the due assignments like the project, your final review, and final exam will be released early in the week. So on Monday, and you will have until Wednesday to complete the final. So you can take it anytime. I will also share lockdown browser installation information. And then the final exam will be password protected. So you will receive a password information in the announcement on the page, and also um, in order to access it, you will need to do that. Okay. And so any extra credit, anything like that needs to be submitted by June 6th. Um, I will extend some of the earlier assignments. If you have something that's locked, make sure you message me and I will unlock it for you so that way you can complete the task. If you're all caught up, right, all you have to do is work on your project, prepare for the final exam, and you should be set for this, the end of the class. I plan to update your grades that weekend. So after you finish your final, I will spend a few days grading projects for all my classes. And as soon as I update your grades, I will send an announcement out so that way you can check out your grade. Okay. And once the grade goes into Web Advisor, you should see it on your transcript or on Web Advisor or EduNav. Now I think that's what you're using. Any question before we start? No question? Okay, let me know if you have questions throughout the session. So in this week, we are going to cover our last chapter, which is on relations. And it's pretty easy. It's going to tie up all the things that we talk about, looking at Cartesian products later on. So to begin, we would start with the definition for relations. A relation is expression to connect objects together. And so it expresses the connection between objects of two sets where two sets may be the same. Okay. And so we can examine whether the relation between objects exists. And so we can look at two sets. So why is this apply? Often that you would see that data sets would have, could be raw data, it could be numerical value, could be strings. So we wanted to be able to examine the objects, could be data sets, and see if they have any kind of relationship, any connection between those objects. And so in the notes, it talks about binary relations between the sets. And so we would start with looking at applying algebraic equations. We would say that, okay, well, let's say that if all your x's value are used, that will be under the domain. And they could be independent values. And you would have the y values as range. And they would be dependent values because they would be dependent on the x. So when you're looking at, if you put this onto a graph, right, you would go across for the x value, and then you would then go up for the y, and you would plot the points. So then when we're looking at the sets, we need to first examine the domain and the range. So in the expressions, we would see that how we denote this, we would have x comma y to represent the pair. And it is an element of R because x is a domain of R and y is the range of R. Okay? And then some of the y could be in B, where some of the x would be in A. Okay? So in the first example, it gives you two sets. The first one is A, where the values is 1, 2, and 9. And the second set, B, you have 1, 3, and 7. So if we're looking at different cases in that, for case 1, if relation R is equal to, then you would have 1 and 1 and 3 and 3 as x and y are equal. Okay? They are equal in values. So when we put this into domain and range, we would say that domain of R would be 1, 3, and then the range of R would be exact 1, 3 as they are equal. In case 2, if we have a relation that is less than in R, then we would have 1, 3, 1, 7, 2, 3, and 2, 7 as you look at how the domain is less than the range. Okay? So then if we take only the x value and list it in the domain, and you only have to list it once if they're repeating, like 1 and 1, 2 and 2. So here, when we bring down the x value, you would list domain of R is 1, 2, as we see that x here is 1, here is 1, here is 2, and here is another 2. Then in the range of R, we would see that there is 3 for y. Okay, another 3 here, so we list it once. And then 7, so we list the 7 for the range. And in this case, what you see is that you would see a less than relationship. Okay, where in the previous case, you would see equal to, where they are the same. Okay, so when you look at the domain, the 1 and the 2 is less than the 3 and the 7. Any question with these cases? Okay, then when we look at case 3, in that it would be greater than. So if you have R is 2, 1, 9, 1, 9, 3, and 9, 7. And so when you look at the range and compare to the domain, here's my domain, x is 2, x is 9. And when you look at the range, y is 1 and y is 3 and y is 7. So when we list the domain for the x value, we would have 2 and 9, right? 2 here and the rest are 9s. And for the range, we would list it as 1, 3, and 7. 1 here, 1 here, 3 here, and 7. So when we look at that, we would say that, oh, x2 is greater than 1, and 9 is greater than 1, 3, and 7. Okay? And when you look at the individual pair, 9 is greater than 1, 9 is greater than 3, and 9 is greater than 7. Any question? No question. Okay. So in the last couple of weeks, last week, we talked about how we would look at graph. And so sometimes you would see relation that could be represented in a directed graph, where in that you would have vertices, right? 1, 2, and 3, and then how it would go from 1 to the next vertex. So the number of the vertices in the graph is equal to the number of the elements in the set, okay? Where you would have 1, 2, and 3 for the elements, where you would have 3 vertices. And so for each of the ordered pair xy in the relation of R, there will be a directed edge for that vertex x to the vertex y. So if there is an ordered pair XX, there would be a self loop to the vertex x. So in this one, it shows that it will be XX, where you would have one going to the other for x to y. Okay? So in the graph, it would be then represented XX as 1 and 1, and then 1 to 2, and then 3 to 2. And that is out of the set 1, 2, 3. So when we look back, we would say 1 to 1, so 1, 1, and then 1 to 2, okay, and then 3 to 2. This should be 2 to 3. Okay. Any questions? So in the type of relations, we would say that there could be an empty relation between sets x and y, or we would represent it as E for empty, and that would be the empty set 0. Okay. Or we would have a full relation in that sets x and y, you would have the product of x and y. And you would have identity relation where you would have x is the set of the large X here. So if you have X, the capital X is the set, where you would have the domain that would be represented as an element of X. Or you would have an inverse relation where you would have B is B and A and B is an element of R. Okay? So then we would examine the relation and we would say, is it equal to? Is it an inverse of? Is there an empty relation or a full relation? So by definition, when we're looking at reflexive relation, we would have to first look at, is it equal to? Is it exactly the same? And if it's exactly the same, then you would have symmetry. And then from there, we would then examine, is it transitive, reflexive, and looking at the properties of that relation. So we would do some practice with this. Okay. So here it says that clearly that it is true that A is equal to A for all the values A. Therefore, A is reflexive. So if it represents the equal to, then you can say that it is reflexive. Okay. So let's do the first question. For number 1, it asks you to determine the range, the domain and the range for the following relations. You have 1, 3, -2, 7, 3, -3, 4, 5, 1, and -3. And what I did was I highlighted in yellow for the x values, and those we would then list them as domain. And for the range, I highlighted in the turquoise. So we have 3, 7, -3, 5. And since we already listed sorry, I got disconnected from Zoom. Let me come back to screen share. Okay, any question with number 1? Okay, so this is pretty easy to start. We simply identify x, y values, x for domain and y for the range. Then in the next one, we want to look at the diagram here, and we want to identify the domain and the range of the elements, okay, how they are related in the form of the function. So we see that there would be, let's say on the left would be your x in orange, and on the right, that would be your range in blue. So we would say that there is a relationship between x to y. So our range would be 3, 4, 5, 6, 7, all of these values, okay, on the left. And then our y, which is our range, would be these values on the right in blue. So you have 2, 1, 9, and 12. So what happened to 3 and 8? It's there. Is there a relationship to x? No, right? Okay, where 12, it's related to 6 and 7. So for the y, we would list 2, 1, 9, and 12, the one with the arrows. Then when you write it out, right, to represent the entire set, you would have 3 to 2. So 3 comma 2. And then enclose that with the parentheses. 4 to 1. So 4, 1. As it would be x to y, right? And then 5 to 9. 5 to 9. And then 6 to 12. So here 6 to 12. And then again 7 to 12. So let's say if this is R, right? Then we would say x of R would be, and then y, that would be related to y of R. Word always auto-correct me there. Okay. Any questions? No, R here is just the name for your set. R just the way that they use R in the text, and I try to replicate it, is relation. So just think of it like a name. You can call it S or Z or something like that. Yeah, it is confusing where this is range, right? But Y, it represents range. Okay. So earlier we talked about what could be greater than, what would be equal to, what could be less than, right? So let's do exercise 3, in that we would examine the condition of the relation in R as the set. Okay. So in exercise 3, it says let A equal to 4 and 6, and B is 3, 5, 7, and 9. Okay. Note the condition of R. We wanted to note the condition of the relation that would be equal to, greater than, or less than. So we would start with A is less than B. And so in the case that A is less than B, we would start with the domain 2. So you list the x2, and we would list the y3. And you notice that 2 is less than 3 there. So that we need to make sure that it's less than B. Then on the next value, we have 4. And when we indicate 4, then on the right, we would bring down the range value. That will be 5. And 4 is less than 5. Next, we would use 6. And we would say 6. Then we'll bring down the domain 7. So 7. So 6 is less than 7. Then again, you don't have to use 6, but since it's the last value, I just reuse it again. It could be that it would be 6 for x, and then the last value, I want to use 9. So 9, and in this case, it's true that A is less than B. Okay. Any question with this part of number 3? Would we not include pairs like 2, 5 or 2, 9? You can. You can expand on that. I just wanted to use these, so good question. So what if I wanted to put 2, 5? Yeah, it's still gonna meet the condition, right? That it would be less than, as 2 is less than 5, or 2, 7, right? Or 2, 9, or 4, 7, 4, 5, 4, 9, and so on. So you get the point. It's as we can then list the domain and the range, and as long as they're less than, the domain is less than, then it's gonna meet the condition that it is less than for the relation. So I'll put dot, dot, dot. Okay. So is there a way that you can make it greater than? Sure, right? You can do 4 to 3, 6 to 5. So we can try that. A is greater than B. So we would start with 4, 3. And then we can do 6, 5. We can do, what else? 6, 3. And then 6, 5 we've done. Yeah. Will we be able to represent equal to? No, right? Because it would then need to be exact. So the way that we would write equal to is going to be 2, 2, 3, 3, 4, 4, and so on. Okay, any questions with 3? Okay, so this one is pretty easy, but I wanted to go through the graph and how that would relate to the definition. So earlier it talks about reflexive, okay? And then we can go through these. So for number 4, it gives you these little drawing or the diagram, and you have to be able to translate that to the property of relation. So it says to determine if the relation R is reflexive, symmetric, and transitive in the following cases. For case A, you have a node, right? The graph that's going to go to itself. So earlier we saw the example. A is equal to A, so then it would be reflexive. And then for B, you have A is to B as B is to A. So we would write that out as A is equal to B and B is equal to A. So that means it's symmetric. Think about mirror when you hear the word symmetric, right? So when you look in the mirror, right, if you raise your left hand, it's the opposite, it's gonna show, right? So when then you would have A is to B and B is to A, then that would be symmetric. So A is equal to B and B is equal to A. Then we would also have transitive for C, where A is equal to B and B is equal to C. Therefore, we would conclude that A is equal to C and A is equal to C. So you might have a relationship where you would say, okay, this is equal to this and this is equal to this. So in the real case example, right? Like, so let's say you have three children and you would say the children A, let's say Adam, his age is 5. The child A is 5. And then Barbara is also 5, right? And then Barbara age is equal to Carl's age. So that means that they're all 5 years old. Okay, so in this case, we look at A is equal to B and B is equal to C. So therefore, A is equal to C. And that means it's transitive. It has transitive property. Any question? Okay. So here it started giving you symmetric example. We see this in our graph exercise that we just done. Okay. And it says that the relation of RAB and BA on the set of XAB is irreflexive. The relation of R on set A is called symmetric. Okay. X is related to Y, where Y is related to X. And the way that we can indicate it with mathematical notations would be like this. Okay. The inverse of X is part of A, and the inverse of Y is an element of A. Okay, so let's take a look at anti-symmetric and symmetric. So in example 15.5, it says the relation R, we have 1, 2, 2, 1, 3, 2, and 2, 3 for the set of 1, 2, 3. And that will be symmetric. So the relation R on the set A is then anti-symmetric if X related to Y and Y related to X imply that X is Y inversely related to X in the element of A. Okay, so if it's the opposite of symmetric, then it would be anti-symmetric. Okay, so here it shows you the symmetric relation, and anti-symmetric is the opposite of that. Then we would have the transitive. We saw this in the diagram earlier, the graph earlier. A is equal to B and B is equal to C. So we can say that A is the same as B which in turn that is the same as C. So A would then be equal to C. Thus, it will be transitive. So in this example, we have xy of R is then related to n, right? X is less than equal to y. And this would be anti-symmetric since x is less than y and y is less than x implies that x is equal to y. Okay, so it is a little bit different than what you've seen in what we saw with the symmetric. Okay. And so if we wanted to make this a transitive, then we would say x related to y and y related to z. And so therefore it implies that x is related to z. Okay, inverse of x, y, z is an element of A. Okay. Instead of just the variable, we would say, okay, the relation R, we have 1, 2, 2, 3, and 1, 3. On the setup A, 1, 2, 3 is transitive. Okay. As we talked about how one related to the other and then that one related to the next one. So the first one is then related to the third. So that will be transitive. And the relation is equivalence relation if it is reflexive, symmetric, and transitive. Okay. So if it is reflexive, right? Like 2, 1, 2, 2, 1, or it is symmetric. I'm sorry, reflexive is 1, 1, 2, 2, 3, 3, and so on. Or if it be symmetric, 1, 2, 2, 1, or it is transitive like this case. Okay. And then for the next example, we have 1, 1, 2, 2, 3, 3. You already know that that's reflexive, right? Where they are equal. And then this one, 1, 1, 1, 2, 2, 1, 2, 3, 3, 2, that's symmetric. Okay, so I'll highlight these for you. And then you have these as symmetric. Okay, and then throughout you have 1, 2, 2, 3, and 1, 3. And then these are also symmetric. Okay, and then you also have this one as I'm overlapping now for transitive. Okay. So it might be easier just to type it out. So in this example, you have 3 of the properties met. Reflexive, highlighted in yellow, where they are exactly the same. Symmetric, where they swap, okay? And transitive, where they would go one to the next, and then that one to the next, and then the third value would then assume be equal to the first. Okay? So that is part of what we call equivalence relation. All right. So let's try the next exercise. And they gradually get a little harder, so just be patient. Okay, so for number 5, it says for each of these relations on the set 1, 2, 3, 4, decide whether it is reflexive or symmetric or anti-symmetric or transitive. Okay, so I highlighted that for you so you can show how the properties would be for the pair. I have 2 and 2. They are exactly identical in value, so that means that they are reflexive. 2 and 3 and 3 and 2 highlighted in turquoise. That means that you notice that they swap, the values swap between domain and range. So that means that they are asymmetric. And then if you look at how it transitioned across, so you would have 2, 3, right? 2, 4, and 3, 4. So that means it is transitive. Any question with 5? A. Then let's look at B and C. Again, we have 1, 1, right? And that is reflexive. We have 1, 2, and 2, 1. That is asymmetric. Okay, and the rest we have 2, 2, 3, 3, 4, 4. So the rest is all reflexive. So to approach this, you just have to know the rule for what is reflexive, what is symmetric or anti-symmetric, and what is transitive. Okay, and then you would evaluate how the pairs would be. Okay, and you can determine based on definition what the pair would represent in property. Then for C, we see 1, 1, 2, 2, 3, 3, 4, 4. Okay, and that would be reflexive. But wait a minute, right? Is it symmetric? So let's go back. Rewind, right? So in the equivalence relation, when we represent this in reflexive, because here it talks about how this would be reflexive, AABB, then the set of A is reflexive. And so the relation of R in the set A is called irreflexive if there's no A in the element of the set A that would be related. Okay, so A related to A is not going to hold. The symmetric relation is a binary relation, and that would be equal to if A B is true, then A is equal to B and B is equal to A. Okay. So then if we examine this, so if they are identical like this, okay, we can say that it would be reflexive relation. So I'm going to change this, take this out. Okay, as it would not be symmetric. Question? No question on 5. And so if you want to be clear, you can type out each, right, each group. Let's try number 6. Okay. So for 6, it asks you to determine whether the relation R on the set of all integers is reflexive, symmetric, anti-symmetric, and or transitive, where xy is an element of R if and only if x is equal to y squared. Okay. So if we're looking at a certain set, and we can say 1, 2, 3, 4, 5, 6, 7, okay? If we say that let x is equal to 1, then y is equal to x if y is 1. So in that case, how do we represent the property for reflexive or transitive or etc.? Then we would have 1 to 1, 2 to 1, 3 to 1, then 5 to 4, 6 to 4, and 7 to 4. And these, the rest of them, will be the transitive. Now, in the case that y is greater than, because if you square y, right, so the only true case that would be if x is 1, then it would be equal to 1, right? Because if you have x, if you let x is equal to 1, then y squared would be 1 squared. That would be y, 1. So that will be 1 and 1. But if you plug in x is equal to 2, right, any subsequent number, it would not be able to meet this criteria. Okay. Unless y is equal to 1, right? So if you say let x is equal to 1, right? And if x is greater or equal to y, then, I'm sorry, let x is equal to 2, then y has to be 1, because if you square 1, right, then you would have y squared is equal to 1. So in that case, that pair would look like this, 2 to 1. Okay, so that will be this one. And then we would try when x is 3, y is 1, then that would be this one. And then we would let x is equal to 5, right? Now, when you square it, if y is 4, if you have x is 5 and y is 4, it would not be able to meet this. Okay, or 6 or 7. So the way that we would probably be able to represent it is only going to be up to here for this equation to work, right? Because if you let 3 is equal to x and 1 is equal to y, then you have 3 is greater than 1, so it's still going to meet this criteria. So any of these subsequent things, I'm just going to remove them because I don't think that they would apply. Okay, then it would not work based on this equation. So there is a transitive if we plug in 3 for x and then y is 1. So we would have 1, 1, 2, 1, 3, 1. But it cannot be 1, 2, right? Because if it's 1 here and 2 here, 1 is not greater or equal to 4. That one is a little tricky. Any question? Now I'm going to type this out now. So that way you know. Okay, so let's work on the next one for 7. It asks you to determine the relation of R on a set of all integers, whether it's reflexive, symmetric, anti-symmetric, and or transitive, where x, y is an element of R if and only if x is not equal to y. Okay, so we cannot say what this condition apply is that it cannot be reflexive, right? Because in the case of reflexive, it would be 1, 1, 2, and 2, oops, and so on, right? So to note that it cannot be reflexive, so that means that it would be irreflexive because it cannot be equal. When you have an equivalence relationship in the values, you would see that it would represent these, like these or these. Okay. It could also be symmetric and or transitive. So we talked about how it would be symmetric because 1 to 2, where x is not equal to y, right? So it meets that condition. and what and x is not equal to y here. So it could be, I'm sorry, it could be symmetric. I don't know why I type asymmetric there. And in the case of transitive, then you would have what? 1 to 2, 2 to 3, right? And then 1 to 3. And then you might have like 3 to 4, and so on, right? Because it could be any integers. Any question with 7? So when you take a look at this problem, what would be best is if you start looking at how the pair would be based on the condition that, or the equation that's given for the relationship, where x cannot be equal to y. So if there is not equivalence, you can start eliminating some of the property, like what we did with the symmetric property. So if it's, I'm sorry, reflexive property. So if it's not reflexive, then it's irreflexive. And so with that, we would then look at how the pairs would be for the other property, like symmetric, transitive. And if it cannot meet the symmetric property, then it would be anti-symmetric. Okay. Any question with 7? And let me save this so I don't forget. And that's all she wrote. Let me double check to make sure if I didn't add anything else for your assignment. So you should be expected to see those type of questions on quiz and exam. They're not that many, just a couple. My dog, she scares me. Okay, so let me double check and make sure that I don't drop anything from between your revision and my revision. Yep, that's all she wrote. So one of the things that I wanted to address also, so you don't forget, there is a discussion thread this week, okay? And it takes place of your lab activity. So if you post it, so let's take a look at it. I'm gonna share screen again. And you don't have to do this right now. You can do it throughout the week. I like for you to have the main post by midweek so that way other people can respond. I wanted to use this opportunity to open up topics related to automata because you will have advanced upper division computer science or computer engineering courses that will tie with this theory. So basically we want to introduce it so that way you are aware of it, you know what it is. And so when you read about it or have to, work on the related topic, then you would know. So here I provided some example and definition. So when you click on Automata Theory and Computer Science discussion thread, I here you would see the description. So automata is a branch in computer science. It's been established for a while now, okay? And so it would really imply the machines that would have the certain features of man completing the calculations more quickly and reliable. So we built the machines to really do our task, right? And the word automaton is closely related to automation, and it would denote the process of carrying out the production of specific processes. It incorporates logic of computation with respect to simple machines, referred to automata. And through automata, computer scientists will be able to understand how machines compute functions and solve problems. And what it means is for a function that is defined as computable, or for the function to be described as decidable. Okay. And automatons are abstract models of machines that perform computation of an input by moving through the series of states or configurations. And that ties back to what we discussed before about state machine. So each state of the computation, a transition function determines the next configuration on the basis of the finite portion that represent configuration. As the result, once the computation reaches an accepting configuration, it accepts that input. And in most general powerful automata is the Turing machine. And this is a favorite topic of most of my students, as you would see the media and a lot of representation for a Turing model, which is fine because it's worth to explore, right, and learn more about it. So the major objective of automata is to develop methods in which computer scientists can describe and analyze the dynamic behavior of discrete system in which signals are sampled periodically. And behavior of these discrete systems is determined by the way that the system constructed from storage and combinational elements, characteristics such as machines, input, output, and state. Okay? So here it basically gives you an overview of what automata theory is, what automatons are, and why is it being studied. Okay, so here it talks about input. That could be input signals or finite sets. You would look at numbers of inputs, and then output would be symbols that will be selected from a finite set, such as set Z, and where the numbers of the output, and state that would go into another set, could be named Q, and that would depends on the type of automaton. So what I want you to do is look at the family of automaton. You will need to pick one, okay? And I want you to describe it. Find some example about it, how it's used. So research it, and then in your discussion, you would tell me which one you pick in the family, and just give me a couple paragraphs, okay, about it, describing how the automaton impact today computational architecture. Okay, so the best thing to really look at is how it's used, what it's, what type of machine it's used for, and so on. And then I want you to include your URL and resources where you obtain the information. And then you can reply to your classmates. You can ask them questions. You can add comments. And so you need to post the main post by Thursday. So I give you some time there. And then just make sure that you have 2 replies for full credit, 2 replies by the 16th, which is Sunday. Okay. And if you want to pick more than one model, that's fine. But what the minimum is just going to be one. So you can look at finite state machine or push down or linear bound or Turing. Okay. As some of you probably seen movies about Turing machine already. And so it's good to explore these things because it really gives you a, at least a very basic foundation. So in the future, if you need to reference it, you can. Okay. And it ties back into the concept of this class. Why do we really need to really explore these mathematical concepts when we're studying computer science? Why is it important? Why is it important in design and development of our systems? Right? So as you look into that, you're going to see how some of these general math concepts would then be applied as we are looking at discrete systems. Okay? Any questions with our discussions for the week? And make sure we do that. All right. Okay, so again, just a reminder, no lab exercise this week. If you have questions or concerns or something you need help with, I will be available on the Zoom link for the Wednesday session. You can stop by. In the past, what my students have done is they bring in their projects. They would ask questions, then they would be able to so I can, like I said, I will not be able to solve some of the issue for you right then and there because I want you to explore and discover and learn. I can give you directions on how to maybe approach it and be able to look at what your existing program and what you can do to further implement it. So I can give you some options and ideas. Um, and then if you wanted to take a look at some example, I can show you some example. I think in this time, um, maybe I will not post the example as much because I want you to be able to do it instead of copying somebody's code. And so that way you will be able to build your strengthen your knowledge and be prepared for the upper classes down the line. But if you want to, get on Zoom and say, okay, Dr. Wen, I want to just take a look at how some people would approach it. I can show you, but I will not be able to post it because I think it's only fair. But there are students that shared their stuff on all over the internet. But like I said, don't copy and paste the code. It's a serious violation in university. They can terminate you from the actual, your program if that's the case. So try to do your own work, collaborate. And if you're working in groups, just maybe coordinate the activity and start early. Do not wait till the last couple of weeks to start working on it. And if things go wrong and then you're going to run out of time because other classes you got to prepare for the finals. So just a little bit every day is going to help. And then go down the list of all the things that you have to do. Okay, any questions? Okay, so before we go, let's see, if you had signed up for like the certification thing with skill sets, it gives you the pin. You can log into the actual student dashboard, but you have to request access to certain course. So you can, I think I'm on the list for the manager for it, along with a couple other faculty. So you can submit it and it's going to send us a notification. I log in occasionally to be able to give you that. I will add you to LinkedIn Learning if you want. So let me know. LinkedIn Learning has a lot of really great tutorial videos. It originally is lynda.com. Microsoft acquired LinkedIn a long time ago and they bought lynda.com. So there are a lot of really great learning resources on there in all different languages, Python, C Sharp, C++, Java, etc. And as you complete those courses, it gives you the LinkedIn Learning certificate, and then you can tie it with your profile. So if you're applying for jobs, you can use LinkedIn to apply for work because there are a lot of jobs showing on there. And then if you have a certain skill set, sometimes recruiter, they actually contact you based on your LinkedIn profile. So as some of you are looking at, how you'll be able to get some internship and jobs from now until you finish at RCCD or even going into the university. And I encourage you to look at summer internship. I've been meaning to put together a list this week. I think I'm going to have a little bit more time. So, but application for internship should be done like around March. Now is kind of late, so you might be able to get internship for the fall or late summer. And every summer, if you do it, by the time you graduate, you will have experience so you can negotiate for more money. Otherwise, if you wait until you graduate, you're going to have downtime in between looking for work. So that will be my advice for you. And then I'm going to put this in the chat. The person that can help you with your resume and things is, her name is Nikki Cook at Moreno Valley. I know at every campus they have a job placement coordinator, and her email is, so when before you submit your resume, or if you have an interview for any job, doesn't have to be, in your field right now, you can reach out to her and ask her to help you kind of look over the resume and help you prepare. And she can make an appointment with you, and then she can walk you through on how to edit your resume. And many of my students had gone through this process, and they told me that it helped them a lot. So it's always good to have another set of eyes to look at your resume, even if you've worked in a field or you worked before and so on. So if you wanted to get some help with that, she's a good person to reach out to and so on. Okay. All right. Any questions regarding the content for today, project things that we have to do, anything? Okay. All right.